Hi class, this is the second lecture for Unit 10, and today we'll be discussing non-parametric hypothesis test. So we saw in Unit 10, Lecture 1, um, what a hypothesis test was and how to use it. And those were examples of parametric hypothesis tests, where the word parametric means it was for distributions with parameters. And we saw, or we know that basically all distributions we've seen are parametric. That is, all the distributions we've seen take in parameters. So for example, the Poisson takes in the expected value, the binomial takes in the number of trials, the probability of success. These are all parameters. So we'll see now that there are hypothesis tests that don't require us to have distributions that take in parameters. So the advantage of non-parametric hypothesis tests are that we don't need to assume that the data came from a binomial. We don't need to assume it came from Poisson. We don't need to know if the data is normal or not. Another nice thing about non-parametric hypothesis tests is that they work with either continuous or discrete data. A disadvantage of non-parametric hypothesis tests is that it's harder to prove significance. So we typically need a little bit more data to do non-parametric hypothesis tests versus parametric hypothesis tests. All right. So we're going to basically see a couple examples of non-parametric hypothesis tests for different situations. And in this class, I'm basically going to skip over a type of parametric hypothesis test called the t-test. And the reason why is I just basically, in most situations in life, it's just better to use the non-parametric versions because it's not always possible to assume normality. And that test, the t-test, requires the assumption that your data population is normal. All right. So, like I said, parametric statistics is about assuming an underlying probability distribution, and non-parametric statistics don't require that assumption. So you may be wondering, why don't we always use non-parametric statistics? Well, actually, often non-parametric statistics are used. It's actually very common. Like I said, though, if you have a small amount of data, non-parametric statistics have a tougher time proving significance. So it's good to assume a distribution when you have small data. And another reason why you don't see it in undergrad statistics is because people think that it's, difficult to understand non-parametric statistics. Um, we're not going to get into the nitty-gritty details about parametric statistics, but one of the sort of fundamental uh, ways that non-parametric methods work is that they convert all data to ranks. So basically, if you have some random continuous data here, like here's some continuous random numbers, they're always converted to ranks. And converting things to ranks kind of removes the scale of the data, and then always turn it into discrete data. So ranks, so converting ranks, like so this is the 7th highest number, the 10th highest number, the 4th highest number, the 9th highest number, is typically the first step for most of these non-parametric methods, and then they're designed to work with ranks of data. So just this isn't, a full derivation of how these methods work, but just wanted to give you a little bit of insight in the steps for non-parametric statistics. So we'll now see a few hypothesis tests that are non-parametric. This first one here is the Wilcoxon's sum of ranks test. This is for comparing two sets of measurements. And the null hypothesis here is that the two sets of measurements are from the same distribution. Now, one of the conditions for this are very loose. The measurements could be different sizes, like you could have 10 numbers in one set and 11 numbers in the other set. The data does not need to be paired, so there's no requirement that you have pairs of data. And the only sort of logical thing is that, if the null hypothesis is that they're from the same population or the same distribution, it kind of makes sense for them to be measuring, the same thing. Like they should both be temperature measurements, or they should both be, I don't know, mass measurements. If they're different things, then this isn't really the right null hypothesis, and this isn't probably the right hypothesis test. So think about this as if you ever have two sets of data, and they're, a valid null hypothesis is that they're coming from the same distribution. The Wilcoxon's sum of ranks test allows you to disprove that null hypothesis or show that they're significantly different sets of data. Now, this is probably one of the most silly gotchas in Skippy, is that Wilcoxon has two hypothesis tests, and they're quite related. So this one is called rank sums. Okay, it's still Wilcoxon's sum of ranks, but it's called rank sums, and we'll see that Wilcoxon's name is used for a different Python function call. So I have some data included for this lecture, and it's some grade data from, gosh, I think 2018, but obviously the grades are anonymized. So one of the examples of a hypothesis test you could do are homework 1 and 2 grades from the same distribution? That is there a significant difference in how the homework looks between homeworks 1 and 2? Now, this is measuring the same thing. It's measuring grades, and you might, I think a valid null hypothesis is that all the homework grades are about the same, but maybe something specific about homework 1 and 2, is different. So I'm showing, maybe this is a little bit of benefit for those of you working on your projects. I'm showing you an example of how to read in a CSV file. Just one moment, I think I want to sneeze. No, never mind. Okay. So this basically reads in the common separated value. One of the things is that these homeworks are point values, and the point value for homework 1 and 2 are different, and I don't want to just prove that. Like that, I know obviously that homework 1 is out of like, I don't know, 20 points, and homework 2 is out of like 60 points, so that's not important to me. What's important to me is the percentages, right? Like if you wanted to compare the grades, it makes sense to compare the percentages. So I'm just showing you the converted it. So here's a histogram of the data. Remember, one of the first things we want to do if we're looking at data is actually plot it. Right? That helps us know that the data is in the right units. It helps us know that the data is meaningful. There's no, errors in it. So I'm plotting the data for homework 1, and basically you can see that most people who completed it got a good grade. A few people did, maybe they only completed half the assignment, and then a few people didn't turn it in and got a 0. Oops. Then here's homework 2, and you can see there's a bit of a different distribution down here. There's a lot of people who got under 60, and then obviously some people didn't turn it in, and then a lot of people who did well on it. So here it is, all the work to get that data. And here's how you do the Wilcoxon sum of ranks test. You put in a list or an array containing your first set of measurements, and a list or an array containing your second set of measurements. And then you just call rank sums, and it gives you the p-value. And so if you recall from the last lecture, the p-value was how you would assess significance. So if the p-value is less than 0.05, it looks like we can reject the null hypothesis. So that in this case, that would mean if the p-value is less than 0.05, these two measurements probably aren't from the same distribution. But here it looks like they are from the same distribution. So it looks like homework 1 and 2 are actually not significantly different. Now we can compare other homeworks. Now here I'm comparing homework 1 and homework 5. Homework 5 was maybe a little more difficult. Like, the highest peak here I think is like a perfect on the homework, or close to a perfect. I mean, in homework 5, that's not the case. But in any case, the p-value for homework 5 to homework 1 is 0.01, so homework 1 and 5 are significantly different. Okay, so that's the Wilcoxon's sum of ranks test. It's literally one line of Python. It's very simple, and it is used to compare two sets of measurements. And I think one of the best ways to think about it, it's valid to compare the two sets of measurements are, is it reasonable that they came from the same distribution? Like, are they in the same units? And they should, it should be possible for you to have different sizes of the data. Like we could have had more homeworks turned in for 5 versus 1. Uh, and if they have to be the same size, then maybe you're looking at data that comes from the signed ring test. So let's talk about the signed ring test. This is for two sets of measurements, but the measurements are paired or matched. Okay. Um, and this one you want to have more samples than the parametric test. That's all this comment is here. So an example of signed data is that we could actually go back to the homework data, homework 1 and 2, but now we could line up the homework so we compare for each person, was there a significant difference between how they did in homework 1 versus homework 2? Now, what is the difference between that? That means that we're no longer viewing the homeworks 1 and 2 as sort of just two blobs of data. We're now viewing them as matched up per student. Another example, maybe another example would be, you know, the maybe uh, how many steps you take per day before quarantine and how many steps per day you take after quarantine. That's an example of things which are paired, right? Because they're paired because each number of steps in quarantine is about you personally before and after. Uh, and it's easier to prove significance when you have data conditioned. That is, if you're going to look at homework 1 versus homework 2 and you conditioned per person, it's easier to prove significance. Or like, let's say you wanted to see if people take more steps before and after quarantine. If you just grab 20 people before quarantine and, I don't know, 11 people after quarantine and try to prove significance, that's more difficult than if you have the same people before and after quarantine with the step data. Okay, so just, a little bit about practically why you would use this hypothesis test. So this one, Wilcoxon-Signed-Rank test, this one's called Wilcoxon. So remember, Wilcoxon has two non-parametric hypothesis tests we use in this class. The signed rank test has his name, and the sum of ranks test does not have his name on it. Okay, so those are the two big non-parametric hypothesis tests. We'll see another one here in a moment, but those are the ones for comparing sets of data, and that's the most common thing you're doing with non-parametric hypothesis tests. So here, like I said, that you could look at homeworks. So homework 1 and homework 2, recall that the original p-value was like 0.7. Now the p-value is 0.087, so it's still not significant. It's not below 0.05, but you can see that we're much closer to a significant result. Homework 1 and homework 5, now the p-value is much lower, so it's much more clear these homeworks are different. Okay, into the last non-parametric hypothesis test, we'll look at a Spearman's correlation test. And this one is for comparing if two sets of measurements are correlated. So we saw in unit 7, I think, how to compute correlation coefficients. And we had correlation coefficients being a number between -1 and 1. And we didn't really have a hard and fast rule. Like if, the correlation coefficient was 0.2, we saw some examples where that meant there was no relationship between the data. And if the correlation coefficient was like 1, we saw some examples where that was meaningful, and other examples where it was not meaningful. So the Spearman's correlation test gives us a p-value, so we can say something like there is a significant correlation between the data, or there is no significant correlation in the data. We cannot reject the null hypothesis. So we still need things to be paired or coming in tuples. But here these measurements should be two different things. So temperature and pressure, person's weight, person's height, number of days in quarantine versus number of steps. And we use the Spearman R Python code to do the correlation. So we'll do another example from the grades, and that is doing well in homework correlated with doing well in the midterm. So we're going to compare the value of your homework grade versus the midterm grade. So again, this this little example just shows you how to, it's a little bit to show you too how to work with pandas. And if for those of you working on your projects, you might be using pandas to read in Excel files or CSV files. So this is an important detail, is plotting the data is nice. Now, I didn't label the axes, I don't think, here. Maybe I'll fix that, but basically the x-axis here is what you got on your homework, your grade, and then the y-axis is the midterm grade. Now you can just visually see that doing well on your homeworks is correlated with doing well on your midterm, but it looks like maybe once you get above a 60% or 65%, there's not as strong of a correlation between your homework grade and your midterm grade, which is kind of interesting. But it looks like if you do really poorly on your homework, you'll probably do poorly on your midterm. But here's the actual data. So the Spearman correlation test, non-parametric correlation test, gives a p-value of 0.005. Right, so we're looking for 0.05. This one's 0.005. So there is a significant correlation between your homework average and your midterm grade. Wow, remarkable. And to compare with correlation coefficient is 0.6. So I think correlation coefficient of 0.6 is right around the number where I would be uncertain if it's significant or not. But by doing a Spearman test, we can get a, a more meaningful number. One thing to know about Spearman tests is that uh, as the amount of data goes up, it's much easier to have a Spearman test. And that's just kind of like how in reality most things are slightly correlated, but it's not necessarily meaningful correlation. So just something to keep in mind is that if you have like 1,000 data points, I think almost, well, not all, but most data at 1,000 data points, there's going to be a small correlation if you're looking at any kind of experimental apparatus. Just a small caveat about using Spearman correlation. Okay, so I just have a little extra piece that we didn't cover in the previous lecture, and that's on discrete parametric hypothesis tests. So we saw the normal and the student t-test. And I think I discussed it too in the class or in the lecture that you can use Poisson distribution for tests or the binomial distribution for tests. So if we view it as a hypothesis by itself, hypothesis test by itself, the Poisson test basically compares a single number, a count, against a distribution where you know the parameter. So the example I think we shared was in lecture actually was if you have a series of factories or chemical plants, and on average they each have like 7 workplace injuries per year. If one particular plant has 14 workplace injuries, is that significantly different than the average workplace injury number? And that can be assessed with a Poisson test, where you know the expected number is 7 and you have a single value 14, and is that significantly different? So this one is kind of like what we did before, where we, from last lecture, where we build an interval and see if it fell into the interval or not. The thing is that your interval should contain your value and all other extreme values. So that's sort of an important detail. For continuous ones, we didn't really care whether or not our value was contained in the interval, because for continuous probability distributions, there is no probability mass assigned to one value, so it didn't matter. But here we actually do care about it, and your interval should contain your value. Okay. So here's an example: is that on average there's 6.3 hurricanes per year in the Caribbean Ocean and the Atlantic Ocean. So this is basically hurricanes that affect the eastern United States. So on average there's 6.3, and then in 2005 there was 15. Was that significantly different? So we're going to construct an interval containing all values as extreme as ours. So it should include 15 and anything more extreme. And when we did the student test or the ZM test, we always had our intervals as being symmetric, like we considered very low values and very high values. Here in the Poisson test, it doesn't make sense to consider really low values. Like we're not that concerned about how extremely low the number of hurricanes is. We're only concerned about very high hurricane numbers. So to do this, we're basically going to say what is the probability of having x at 15 and greater for the Poisson distribution. And we can just do the trick of basically we want to sum up all of these things. We can just look at from 0 to 14. So 1 minus 0 to 14. So this is the complement. So rather than trying to get the sum of everything from 15, 16, 17, 18, etc. up to infinity, we can just do 1 minus the sum from 0 to 14. So you can plug in the equation for the Poisson distribution, but I just use CDF here. And then I'm just evaluating what is the cumulative distribution function of the point 14 with a mu of 6.3. Where does it, why is it 14 and not 15? It's not 15 because I want to keep 15, I'm doing the 1 minus trick, so 15 should belong to the other interval. Okay, because remember we want 15 to be in the interval that we're computing the probability of. So with a p-value of 0.002, that means that in fact 2005 was an unusual or significantly different year for hurricanes. Highly. All right. So I think that concludes what we'll cover for hypothesis tests. So we saw parametric, non-parametric, and then within parametric we solve for continuous and discrete, and they're pretty straightforward. You just find an interval that's as extreme as your value and include your value in the interval. And for the non-parametric, it's even easier. We just basically call Python functions, and they give us back p-values directly. All right,